In the kingdom of Linux, there is one ruler who answers to no one. A king seated on the throne of UID 0. The superuser account established at the dawn of every system, wielding absolute authority over every file, every process and every device. Root's power is total. Read any file including password hashes. Kill any process including the system's own heartbeat. Bind to privileged ports below 1024. Load kernel modules directly into the heart of the machine. Bypass every permission check, every audit log, every firewall the kernel can muster. The Linux kernel implements this through a fast path bypass. When the kernel sees UID 0, it skips the capability checks entirely. One identity, one number, one crown, and the entire kingdom bends to its wearer. And here lies the catastrophe. Many humble servants of the kingdom need only one small privilege to do their duty. The ping program merely needs to send a raw network packet. Yet under the old decree, to grant that single power, the king must hand over the entire crown. This is the dirty secret of Setuid root binaries. A program needs one capability, sending ICMP packets, binding a low port, reading a hardware clock, but inherits the full might of root. Every file readable, every process killable, every kernel module loadable. The entire arsenal, bundled with that one tiny task. The risk is catastrophic. Any vulnerability in that Setuid program, a single buffer overflow, a single misplaced pointer, hands the attacker the crown. One bug in ping, and the intruder owns the entire kingdom. Read every secret. Plant persistent backdoors. Rewrite the kernel itself. This is precisely why the kingdom needed reform. Granting total power to perform a single task is not security, it is a single point of failure wrapped in a crown. The old model made root the most dangerous account on any Linux system, and every Setuid binary a potential kingdom-ending vulnerability. Once upon a kernel, there was only one crown, the crown of root. Wearer of the crown equaled UID 0, equaled total dominion over every file, every port, every process on the machine. Absolute power, absolute danger. The all-or-nothing problem is the real villain here. A binary ran as root and could do literally anything, wipe disks, intercept traffic, rewrite logs. Or it ran as nobody and could barely read a file. There was no middle ground, and that's a security catastrophe waiting to happen. Linux capabilities shatter the crown into roughly 40 discrete gems. Each gem unlocks exactly one privileged operation, nothing more. Hand a servant only the gem they need, and the rest of the kingdom stays safe. Meet cap_net_bind_service. The silver port-shaped key engraved with port less than 1024. This gem lets a process bind to the trusted low ports. HTTP on 80, HTTPS on 443, SSH on 22. Web servers need it, and now they get exactly this gem and nothing else. cap_DAC_override. The master key that bypasses file permission checks. DAC stands for discretionary access control, the normal read-write-execute rules on every file. With this gem, a process can read or write any file regardless of the permission bits, which is exactly what a backup daemon or log collector needs. cap_sys_admin, the heavyweight admin badge. This gem grants the ability to mount file systems, manipulate namespaces, and perform a long list of kernel-level operations. It's so powerful it's jokingly called the new root, which is why you grant it sparingly. cap_net_raw, the smallest, humblest gem of the bunch. It grants raw sockets, the right to craft custom packets and use ICMP, which is precisely what the ping utility needs to send echo requests and listen for replies. Now the payoff, a humble servant named Ping walks before the king. Ping needs only to send one echo request. The king reaches into the pile of shattered crown gems and hands over exactly one. The tiny green cap_net_raw. The full crown stays on its cushion. Ping bows, equipped with precisely what was needed, and nothing more. Every running process on Linux carries 4 labeled buckets of capabilities, plus one ceiling that hangs over everything. Together they answer one precise question. What is this process allowed to do right now, and what could it ever become? The effective bucket holds the keys the process is actively wielding right now. When the kernel checks whether the process can open a raw socket or bind to a privileged port, it looks here and only here. The permitted bucket is the full keyring. Every capability the process is allowed to raise into effective when it needs to. It is the upper limit of what this process can ever become on its own. The inheritable bucket holds loose keys dangling on the belt that survive across an exec call. When the process runs a new program, the kernel ANDs this set with the file's own inheritable set to seed the new permitted set. The bounding set is not really a bucket. It is the vault overhead. The system-wide ceiling listing every capability that could ever exist on this machine. No exec, no privilege escalation, No Setuid can push a process above this line. When exec runs, the transformation is precise. The new effective starts empty unless the file is marked inheritable. The new permitted becomes the end of both inheritables filtered by the bounding ceiling, and bounding itself never moves. Ambient is the bonus fifth bucket. Capabilities copied directly into both effective and permitted of any unprivileged binary the process spawns, with no file cap gymnastics required. It is the convenient shortcut, still clipped by the bounding ceiling. Effective is the keys in your hand. Permitted is the keys on your keyring. Inheritable is the keys you can hand to your child. Bounding is the vault of every key that exists. Once you see the 4 buckets and the ceiling, capability management stops feeling like magic and starts feeling like a lockable tool belt. Linux capabilities split root's all-or-nothing power into discrete permissions. The classic example is ping, which needs raw network access without needing full root. We'll prove it by inspecting the binary and the shell's own capability sets. The first inspection uses getcap to read the security.capability extended attribute on the ping binary. The output cap_net_raw plus EP tells us the file carries the cap_net_raw capability in both the permitted and effective flag sets, which is exactly what ping needs to send ICMP echo packets. Next we read the running shell's own capability sets from procs. Every process exposes its current capability masks in /proc/self/status. When we grep for cap, we expect to see all zeros across cap-inh, cap-prm, cap-eff, cap-bnd, and cap-amb, confirming this shell has no inherited privilege whatsoever. Capsh print gives a more human-readable view of the same information. The current and bounding sets are both shown as empty, and the securebits flags confirm no ambient or file capability inheritance is in effect. The shell is completely unprivileged from a capabilities standpoint. Now we look at the file permissions of ping itself with a less la. Critically, there is no s in the owner's execute position. The string reads rwxrxrx, meaning the Setuid bit is not set. If this binary relied on the old Setuid mechanism, we would see an s instead of the third x. And here's the proof. Ping runs successfully against localhost as an ordinary user. No Setuid bit, no inherited capabilities from the shell. Yet it can open a raw ICMP socket because the kernel honors the cap_net_raw file capability stored in the executable's extended attributes. This is precisely the security improvement file capabilities were designed to deliver.